Okay, worksheets. So last time we just started to discuss about gradients and loss functions and all of this good stuff. So let's solve some problems related to derivatives, gradients. I assume everyone took multivariate calculus at one point or another. So you heard about gradients, you heard about partial derivatives, you heard that function has partial derivatives and they are continuous, then they give the gradient. So this time it's just about calculations. So this problem is just about calculations. So just to practice thinking about how these gradients look like, what do they do? So there is this function. It's on the top. It has two variables, x and y. And somehow it feels very symmetric in x and y. It kind of behaves the same way. And it's sum of these two other functions. And we need to calculate its gradient. And to calculate the gradient, we can calculate the partial derivatives and then check whether the partial derivatives are continuous at the points of interest. If they are, then we found the gradient. Otherwise, the gradient might not exist. OK. So this question, first part, is asking what's the gradient for f defined above. So just a little calculation. You have paper or a notebook or something. So let's do this. You have, I think 5 minutes is very generous for this. You have 5 minutes to answer these two questions for yourself, and then we're going to discuss the answers. Go. It's going to be good for you to try to do this on your own. One more minute. All right. So this is the function. xy leave on the reals. Who wants to do the gradient? Shibunaka?
The gradient has two parts. It's got its, with respect to x, I don't know what I should write up here, delta of x, y. And it's got the other part with respect to y. Let's start with part with respect to x. The gradient there is, well, the function there comes in two parts, and because like derivatives are, I don't know the word, it distributes over addition, so we can just look at the two parts separately. First, we're looking at derivative of this with respect to x, and so I find it easier just to expand that. And then this is invariant with respect to x. This is derivative with respect to x is 2y. And this is derivative with respect to x is 2x. And it's symmetrical for y, so when we get to y, we'll do the same thing. As for the other part, can you write it here?
Okay, sure.
E to the xy. I might be wrong about this because I don't remember calculus super well, but I think when you differentiate e to the ky, just take that constant and you multiply it. Well, we're differentiating with respect to y here. So the upshot is that you just get that part. So plus y times e to the xy for x. And for y, it's the same thing for both sides because it's a pretty symmetrical problem, except instead of pulling the y out, you pull the x out. That's what I got.
Okay. And so if you put these two into vector,
And
then that would be the claim that gives you the gradient of f.
yeah, that's fine.
Do we know that this is a gradient? For sure?
Well, both functions are differentiable and the transaction.
Yeah. So in order to know that this is really the gradient and the gradient exists, we need to argue that the partial derivatives are continuous.
Okay, I can argue that they're continuous with respect to
Everything.
which variable? every variable. Start. They're kind of the same. I'm only going to look at one side. So this is continuous with respect to both variables, right? It's constant with respect to y. It's linear with respect to x. This is the same thing for y. This, like the exponential function, is continuous, and when you multiply a continuous function by a linear function, it's still continuous. Continuity distributes over all of that.
Okay, sure. I mean, this is not a calculus class, but so there is an argument that you can make that both of these functions are continuous. Good. Yeah. And then we are done. So basically do the calculation and then just note that the partial derivatives that you obtained are continuous functions of the variables, and then you're done. Thank you. Second part was the gradient of f at 0, 1. Okay. Someone else. Okay, let's see. Right. 3. I got the 3. The 0. And yeah, so from here we get 2 in both cases. And then here for 0, we get 1. And here we get 0. So yeah, you're right. 3, 2. All right. That's good. Thank you. So why do we need to check that the partial derivatives are continuous? That's kind of awkward if we have to say that. So here's an example. It's kind of a classic example for why do you need to check this. So we need 2 variables at least. So there is x, and there is y. And then, like you have your function. This is your z. So it will be a surface, right? It's kind of like hard to draw, but like there is some surface. You can look at this surface from above and kind of think about it as a map and just draw the elevation curves, like the ISO curves, where the elevation is the same as in a map. And you can also draw a function like that. And so for this example, it is better to just think about this elevation curve. It's not a very beautiful function. That's fine. So here's from above. You have x and y. You had some like ordinary function like maybe this one, x plus y squared. So that would be just a quadratic function. Then the curves for this would be like this, right? So this is how, something like this. It's like higher elevation if you're going away. Is it how it is? I hope it is. Maybe that's like x squared plus y squared. That's x squared plus y squared. That's how it looks like. These elevation curves rings a bell. It makes sense, right? OK, so our function is going to be O0 except we introduce some deviation from this O0. So the O0 function is very simple, no elevation curves. It's like everywhere 0. But here we're going to take this one curve when y is equals to x squared. OK? And along this curve, we just set the function value to x. So I don't know, maybe it's like this is 1, this is 2. So here the function value is going to be 1. Here the function value is 2. Here goes 3. So it's kind of just increasing linearly along the curve. So here, it's -1. It's -2. So it's like, okay, the elevation curves really look like funky on this one. So you can try to imagine like how this function looks like. There is a big ridge here, and it just like sticks out, but it's like infinitely thin. It's a weird function. Nevertheless, it's an okay function. What are the partial derivatives of this function? So the function is fxy um, 0 when y is not x squared, and x when y is x squared. So what are the partial derivatives of this function at, let's say, 0? So we're talking about whether this gradient exists at all. And for this, we can calculate the partial derivatives. So we can calculate the partial derivative with respect to x first. So what's the meaning of partial derivative with respect to x? It's like you kind of just take, like we are at 0, 0. Okay. So you take the origin, and you just look at how the function behaves along the x-axis. How does it behave? Well, it's a very simple function. It's identically 0. Okay? So you have to take the derivative of the identically 0 function. And of course, it's a constant function. Its derivative is 0. So this is just 0. So now do the same with respect to y. So now we are talking about the function restricted on this line. We are at 0, 0, and we are just moving along the y-axis. How does this function look like? Well, if we do all these restrictions, then this function is just identically 0. Because here, okay, we are on the blue part here. But in this blue part, we are at 0. X is equal to 0. So even on the blue part, where you have these exceptional values, exceptional assignment of values, you get 0. So everywhere else you have 0. And here you also have 0. So this function along the y-axis also just identically 0 function. And so the derivative of that function at 0, when y equals 0, it's also 0. It's a constant function. Its derivative is 0. So now, does this function have a gradient? What's the meaning of the gradient? Who defines this gradient? What's kind of the intuition behind the gradient? Who remembers that? Okay. Does it help us? Say this? In a way, it's like not very intuitive, right? Like you just said, it's multi-dimensional derivative. What does it mean? Well, maybe you can expand. What's the definition? What do you mean by a multi-dimensional derivative? What do you mean by this derivative thing?
The derivative exists where the function is well, it is different.
Sure.
Gradient is defined as
Okay, so going back to first encounter with derivatives. Usually people draw this, okay, it's going to look like that, but it's just like one-dimensional. You draw a function like this, and when derivatives are introduced, let's say at some point x naught, so there's only one variable now, call it x. You have this function. What's the picture that people draw? It's a tangent line. So if you can draw a tangent line to the function, then the derivative exists. What does it mean to draw a tangent line? So that kind of means that if you zoom in around this point, this function behaves very closely like the line. And as you're approaching that point, the function really, like the deviation between the function values and the values that the line gives you, they diminish. They go away. That's the meaning of a derivative. If you are in any number of dimensions, the meaning is not changed. You want to have a derivative, then you can represent the function with something really simple. Cannot be a line, because if you are in multiple dimensions, like you have 2 dimensions, then you need something as. The generalization of that is going to be a plane if you are in 2 dimensions, and it's going to be a hyperplane, they call it in a very elegant fashion in mathematics, if you're in multiple dimensions, more than 2. So basically, so what are these like line and hyperplane? It's just like if you're moving along here with the deviation from x naught, everything changes in a linear fashion, right? Like it's a linear approximation that you're coming up, and the linear approximation becomes infinitely precise without any limits, like as you're approaching the point of interest, x naught. At that point, the approximation should become very, very good. Doesn't matter how I'm approaching x naught, it should be good. So going back to our example here, we have this really weird function. It's like all flat. This is kind of sticking out, and then this is going in, right? So now I have to fit a plane to this such that no matter how I approach things, this plane is a good approximation. So which plane to fit? Well, calculating the partial derivatives, you would think that it's like the plane that is just parallel to the whiteboard. It's like the identically zero plane, right? So okay, if I flip this around, like this is my z-axis, and here's a plane. This is the plane that you would fit to. If the function was everywhere 0, this is the only plane that you can imagine that's going to work. And this is what partial derivatives are going to give you. But now there is something funny, because if I approach this function along this curve, just focusing on this curve, when y equals x squared, then the plane is it's kind of sticking out, right? I don't have a notebook. I don't think that you can really plot this function. Huh? Well, yeah, the plane. I mean, you can imagine a plane. Okay. Yeah. So you need to have that even if you're approaching along this line, then we get good approximations with the plane. And okay, if you do the calculation, then it happens that that's not true. So The derivative doesn't exist at 0, 0. Okay. Maybe we can try to draw it later, but it's I don't want to venture there now. Yeah, but like this is a discontinuous function. They will not do anything with it. It's like you really have to code it up to see anything. Because the graphing calculators are prepared to show you nice and continuous functions. And this function is all but continuous. It's about ridges. Yeah. Right. Anyways. All right. So now we have all these other problems. Find the gradient of f for the following functions. We have more variables. We have to remember the rules of calculus and all that. So let's do this. Okay. Maybe another 5 minutes. Oh. One more minute. All right. Okay, before we do this, I have to go back to this example. I think, yeah, I confused myself about this, and it was totally wrong. You should have told me. I don't understand this. Stop. What? Everyone saw the plane. I saw the plane. I saw that I understand what's going on. But then I was like, okay, this doesn't make any sense. For the function that I was proposing, the 0, 0 plane is totally fine. It's like you're going to approach it like along this line. It doesn't matter. That doesn't work. The function should have been like this. It's almost everywhere x, except that if you're on this curve, then you get a value of 0. And so now you can imagine, okay, how does it look like? XY plane. Here is where x is, okay? So it increases. It's like along y, it's unsensitive to y, except that there is this special curve in the plane where I make a surgery on this plane to push down the values to 0. So there, along that curve, I have just this 0. It's kind of like sticking out. I still cannot draw it with a graphing calculator because it's discontinuous, but you can totally imagine what's going on. And now we understand, okay, partial derivatives along x. What is it? It's like 1. It's increasing. It's not sensitive to y. It doesn't matter where you are. The derivative along x is 1. Derivative along y, it's 0. Okay, because it's insensitive to traveling along the 0 axis. Can we fit a plane at 0, 0 to this weird function? Not really, because the plane has to satisfy two things. It has to be the same as this plane on one hand, and there is the other plane, which is just given to you by this y equals x squared, and there the values being 0. So because of that, you need to have the identically 0 plane. So we need to have two planes. Because if I approach along the y equals x squared, 0, 0, then I'm on this plane, and otherwise I'm on this plane. So the two things are not compatible with each other. Therefore, we don't have the gradient. Okay. This should make a little bit more sense. Okay.
What is really the difference between that example and the previous one, other than which side is yours?
Oh, the previous one was, I mean, there it was an identically zero function. And along the y equals x squared, I was creating the sticking out. It goes up to infinity when x is increasing, and then goes to negative infinity when x is decreasing along the curve. So along this parabola, it would be like going down, coming up. And otherwise, it's 0, 0. And it has the unfortunate property that along the parabola, when you're approaching 0, it's kind of like that also kind of approaches 0, 0. So the 0, 0 is totally fine, I think. Oh, no. OK, so yeah, you're right. It's like you have the OK. So you should have OK. So if I just think about the y equals x squared and how the function restricted to that looks like, so now it's the y equals x. And so that's the other plane. Oh, so that example is also good, but it's harder to see. Yeah? OK, so think about again. So the odd example, if I take the identically zero plane, what has to be true that no matter how yeah, so the odd example also works, because if I just focus on the y equals x squared, then the correct plane would be the plane that is just the y equals x plane, or the plane that increases along x. Yeah. Okay. Right. And the reason this is not easy to feel that much, because I was very sloppy when I'm explaining what it means that this tangent line is approximating this function well at that point. Because that kind of just means that if you take x naught, this is fx naught, then you can write this so that the value that the line takes is with some coefficient a equal to this. And the error between this and fx should be little o, the deviation between x and x naught. So it cannot be proportional to the deviation. It has to be smaller than that. And that's kind of like hard to capture with an intuition. It's like you really have to calculate it. It's like so to give you an example, if you have this function here, then there are many planes that you can put at this kink. And okay, so the deviations here are decreasing as x approaches here, x naught. But that's not enough, because the deviation is decreasing proportionally to the distance to x naught. It has to decrease faster than that. So it has to be a lower order error. And that's what is not going to be satisfied in these examples when you're fitting the two planes. All right. Okay. Not much time remains. So maybe just discuss the very first one. Maybe the last one. Why the last one? Okay, then if you want to discuss the last one, maybe you should discuss the one before. Okay. Okay. So here, in both of these, x is a vector. Okay. So it's not x, y, and z, but x1, x2, and so on and so forth. Different notation, but same idea. And okay, let's do 3. So you're interested in the gradient. You calculate the partial derivatives. You check whether they are continuous. If they are continuous, you're good. If they're not continuous, then you're not good. Usually, it's going to be continuous. So there is this function. It's a function of x. And we need to calculate the partial derivative with respect to all the variables. Let's just take one of them. So let I be between 1 and n. So let's calculate this. So just write the operation. And here, there is this x transpose b. So x transpose b, what is that? That's the inner product between x and b, or beta. Okay? So that's the sum of the respective product of respective components. And here, I could make a mistake by writing that this is the sum over I going from 1 to n of xi and beta I. And the mistake now is that I'm recycling index I for two purposes. I fixed I, and I said I want to calculate the derivative with respect to variable xi, but now in the sum I'm using the same. That's very confusing, and it's not going to lead to anything good. So is I fixed? Is I not fixed? It's like I was fixed, so I can't use it. It's that variable is taken. Would be a clash. So use a different variable. It's like something to pay attention to. And then derivatives distribute over sums. So this can move in. All right. And then here we just have to look at, OK, we have this expression. It's a product of two things. We are interested in sensitivity with respect to variable xi. So when j is not equal to y, this is just a constant here. As a function of xi, it takes the constant value. So if I take its derivative of a constant, that's 0. So if j is not equal to I get 0. When j is equal to I, then you imagine, OK, this is xi times beta I. Take the derivative of that. OK, linear function. That's just beta I. So you need to collect all of this into a vector. And if you find that that thing is a continuous function, then you're done. You have the gradient. And this is constant, so it's continuous. Constant is continuous. You have the gradient. And you can just write this is equal to beta. OK. So calculating this, you can do the same thing. You would just write this. But you can imagine that, OK, this is a composition of squaring and then this other function here. And so use the chain rule for derivatives. The derivative of the square function is 2 times the function. What is the chain rule? The chain rule just says that if you have 2 functions, you're composing them. Taking the derivative is the same thing as a derivative composed with the original function times the derivative of the function, or the inside function. So that's chain rule. So here, you take fu equals u squared. The derivative of that is 2u, 2 times u. The g function is whatever. It's like what's inside x transpose beta minus y. So f prime, so that's 2 times what's inside. That's x transpose beta minus y times the derivative of this. You take the derivative of this, then, OK, negative, subtraction, addition, distributes over derivatives. You take the derivative of this, derivative of that. You can just go step by step. And we have already calculated the derivative of this. That's just beta I. And the derivative of this is going to be constant because y doesn't depend on xi. Right? So if you collect all of this, then you find that the answer is that you can pull out this from the vector, and then you just get this 2 times this other constant times beta. Okay. Chain rule. OK. All right. Next time, we continue with something else. I think we got enough of derivatives today.